Thanks, everyone. Yeah, welcome to my talk on automated testing. So as said, I did indeed hand draw slides. I was asked like, "Hey, you want to give a talk?" I was like, "Yes, but not about anything I usually talk about because I'm gonna go on vacation soon." So I was like, "I want to do something fun," and I was like, "I'll hand draw slides about a topic I don't talk about a lot." So welcome to my hand drawn talk, and I hope you can read my handwriting. If you can't, I'm sorry. So yes, hi, I'm Yosh. I work as a developer advocate at Microsoft. As part of my day job, I work on async Rust. It's one of the things I do. Effect Generics, the Effect Generic Initiative, I co-lead. And more recently, I've been very involved with WASI. The new Preview 2 should be shipping in the next couple of weeks, I want to say. So expect interesting WASI things to hit the front page of whatever your favorite website is soon enough. But yeah, I won't be talking to you about any of that. I won't be talking to you about my two cats either. Instead, I'll be talking about testing and how we maybe can do better, some interesting things about testing. I've been thinking a little about testing recently. Um, so I recently learned this term called shift left or shifting left or left shifting things. And I thought it was very interesting. And I was like, oh, I reckon maybe some other people haven't heard about it. If you have, I'm sorry. If you haven't, maybe you'll like it. Or if you have, maybe this is an interesting way to look at it. But it's roughly like coming from a point where we acknowledge that we make mistakes. So when we write software, like we all make mistakes, right? Like sometimes the mistakes are big and important and like cause critical failures, and sometimes we're like, whoopsie, forgot a semicolon, and that's all okay. But like the difference isn't so much in that we make mistakes, and it's not a bad thing that we make mistakes. We should acknowledge we all make mistakes. The only real difference is when we find out about the mistakes. So the slowest way to find out about a mistake you've made is when a customer or a user approaches you and says, "Hey, my thing is broken, and here's why." And you're like, "Oh my God, thank you for reporting that," and that's so good. Sometimes you notice like, "Hey, my subscriber count or my user count is going down." Probably something's wrong and you're guessing why mistakes happen. So a little bit easier or a shorter feedback loop is if you hire a bunch of people and you tell them go find a bunch of mistakes, and then they come back and they find mistakes, and they're like, here's bugs, and then you get to fix the bugs. Even faster is if you have tests, because then you're like, hey, you wrote some code, you check it in, you push it, and then tests come back and they say, hey, tests are broken. That's even faster. Like the fastest is when your compiler tells you things are broken, or Rust Analyzer says, hey, this is not going to work. That's immediate feedback almost. And so shifting left is the idea of bringing things that are slower to feedback cycles that are faster. And with the core idea, the core principle being that we cannot mitigate mistakes. Like human error is a constant, is a real thing. The only thing we can control is how we get that feedback, and a continuous effort to push it further to the left. And that, using Rust is one of the ways that we can shift left, where we go from an interpreted language that is doing all these runtime things to a compiled language that catches more things at runtime with type safety and all these cool things. I'm sort of bringing this up because when we try and justify to management how we would like to write more tests, and oftentimes we get management's like, no, I'd like you to push more features instead, and it becomes this very sort of difficult conversation, because we as developers, we understand tests are good, but why are they good? And a way to potentially frame this is to be like, well, tests are good because they help us shift left. They bring costs down from these very expensive feedback loops. User reports are potential to lose users, or QA teams, they're very expensive time-wise, to further left to these cheaper feedback loops, ways that cost us less money, that allow us to have less overhead fixing bugs because we catch them sooner. So that's the framing around shift left. And oftentimes my talks are about things we can add to the type system. So it's all the way on the left, new type system extensions. Here's structured concurrency, or all these fun things. And I kind of want to talk about one step up, which is well, we can't always add everything to the type system. There's limits there. So what is it that we can do in the next step up? How can we be better about how we test? What are strategies in which we can test more thoroughly, reduce the cost of testing, make it easier to like have more coverage, those kinds of things. That's sort of what this test is, or this talk is about. Um, so with that framing out of mind, I can scroll further down to like, yeah, roughly, like one sort of like key question that we should be asking ourselves is like when we write unit tests, we're writing for test cases that we can conceive of. We're like, well, what should this function do with, I don't know, this one input over here? And then maybe you think of a second one, third one's often stretching it, but then like what are the bugs that we haven't thought of? Like what happens when we have a memory allocator and we find a perfect like segment where two things interact weirdly, or like we write our email validator and we forgot to test a particular character. Like all these things that we haven't thought of is how do you catch bugs like that? Because when you put your code out in the wild, like people will be using it and eventually they'll start hitting things or interesting interactions between things. So at the core, like automated testing is about finding ways in which we can test more thoroughly, create more tests so that we can also catch the things that we didn't even think like could be bugs, but oops, they end up being bugs. So, that's automated testing. And roughly the driving idea behind automated testing is if the top flow here is like where you're a developer and you're writing a test, then you write some code and at the end of it you have one test. However, if you flip it around and you instead of like writing a test, you write a test case generator, which hopefully is not that much more effort, but like, assuming it's not much more effort, then we have a potential infinite amount of tests because rather than generating one test, we've created a thing that generates tests for us, and now we can test a lot more. I promise this is not an AI talk, that this is actual like, engineering based things. I'm not saying like tell the LLM to write you tests and now you've got tests. No. It's how do you do this like manually? So, like okay, great. I've told you like write yourself a test case generator. Like, how do you even do that? Like, where do you start? Like, what is a useful way of doing this? Sometimes you see people like writing test matrices where it's like, I've got two inputs here, or like a series of inputs there, and another like, other thing for each case, test every single case. And now you've got a matrix of like a bunch of possible cases. Like it goes one way, but test automation oftentimes like uses randomized inputs, so like a full random deterministic seed and permutations on that. Things that oh shoot, I should have like changed the ordering here, but you may have heard words like fuzzing or fuzz testing, or property testing, which I believe has a different name as well. Another one, I forget what it's called. Doesn't matter. But those are variations. Those are things, the subgroups of like automated testing. And so when you're going to write an automated test, there are three interesting like practical strategies that I want to share here. So I'm sorry, maybe it's a little dry, but I'm going to give you a little theoretical overview of like, here's ways to think about it. And then I'm going to show you some code that I wrote with this, and then hopefully it'll make more sense. Or not, and we'll find out. But yes, round trip testing. So that's number one. So round trip testing is, say we're writing a data format or a parser or a serializer or any sort of thing. What we can do is it's a very simple thing where we say like, hey, parse a color over here and then encode the thing again. And we say like, if you parse it, then you have your type comes out of it. And then you tell the type, please encode. And then you get your data back out. And then you compare the original data versus the now like new data. And then you can be like, okay, is my parsing and serializing, if I do that like in a round trip, do I end up with the same thing? This is useful for anything that deals with like user input or like, your way like need to serialize and reserialize things. It makes some assumptions, but roughly speaking, this is a very like low effort way of testing that. Like for any given like random image, if I can generate a random image, can I parse it and then encode it, and do I end up with the same random data? So that's one. Differential testing is another fun one. I kind of want to show a demo. Let me see if I can switch screens. So I can make this a little bit more relevant. So I can like point you at a thing. I'm like, here's how you do this thing, rather than like, here's the theory of the thing. Hold on. Can we switch screens? I'm very sorry to the organizers. Did someone say technical issues? Because okay. We're gonna share screen again. Allow to share screen, and then we are going to share this screen. Can you see my screen again? Perfect. Perfect. Because now I can drag a little window on there, and then I can show you a round trip test, I think. Can you see my little browser window here? Okay. Font might be a little small, but we can fix that. Okay. You should be able to see this, yes? A little more? A little more. Okay, we can do that. Sorry, I'm going to expand it more. Even more? Okay. all right. We're gonna try like this. Can I can't click that element away. Okay, so to give you an example here, this is a crate that I've written for fun called HeckCheck, which uses the arbitrary trait. I'll try and tell you more about that in a second. But arbitrary is like a thing you can derive. You can put it on your structs or structs, enums, whatever, ADTs. And now you can tell it like, please generate me a random version of this thing. And like kind of like all the derived things, it's like recursive. So here we say we have an RGB struct that we're gonna fill with like random like R, G, and B values. And then, impl RGB, we give it two methods. To hex, which converts it to a hex encoding, and a parser, so as a serializer step and a parsing step, deserializer step, which says like, hey, given a hex string, please, decode it into an RGB value. And now using HeckCheck, we can do a round trip test right here. So we say, hey, construct me a new RGB value. And it says anything that derives the arbitrary type, I can construct because it knows how to. And then you have a new RGB value. And then we say, please convert it to hex. And then we say, please convert it back from a hex to, we start with the structure type and we convert it to a hex string. Then we parse the string back to the original type. And then we assert that both were equal. And that is a round trip test there. We start with the structure type, went to the data, ended back up with the structure type, and then checked for equivalence. Round trip testing. It's one strategy. And this will check like using a random number generation. It'll like walk through a series of permutations. And every single time you run it, it'll be different, but it is seeded. So you can always like be like, hey, if this thing crashes, it'll be like, hey, I ran with this seed. And then you can like check back like, okay, what values did this thing crash with? So that, is automated testing. We only describe what the assertions are, and then we leave the random value generation. We leave that up to a framework, essentially. And this can be, so I'll explain more in detail, but like you can substitute this with a fuzzer too if you want to. All right. Anyway, that's round trip testing. That's one strategy of automated testing. Second strategy, differential testing. And this is probably my favorite one because this applies to like pretty much any interesting thing you can do with this. So rather than doing a round trip where it's like one random value, is we tell the random, like our source of randomness, to not generate instances of types, but to generate commands, generate operations. So say we are implementing our own data structure, a data structure which is semantically equivalent to a vec, but it is implementation-wise, it does something else. It might be like a vec of bools and we like store it as a bitmap. It's a different representation, but we can model it as a vec of bools. What we can then do is we can create an oracle implementation, is what it's called. It's our thing to check against, where we say like, hey, we know the semantics of this thing. And on the other side, put our implementation and then check that all the operations are equivalent. So if we say, hey, read the value or read to position 12, write to position 8, delete from position 10, read from 6, and then read from 8. And if these two things don't check, then we panic and we say, hey, here's the sequence of operations which led to this failure. we expected our oracle to have a particular output, but our implementation had a different output using these commands. And the cool thing that like automated testing frameworks tend to do is they tend to shrink it down. So they'll try different, once they hit a failure, they'll try different permutations to try and like reduce the series of like commands down, to reduce the random data down until it finds the smallest it can within a reasonable amount of time. So to show you an example of how I use this, if I can find my browser window, nope, wrong browser window. Is this you? This is you. There we go. Oh wait, here's the other one. Yeah, there we go. Or not this one. Here. Yeah. I prepared these like ahead of time, but I'm sorry if they're little. Is this legible? Yes, great. Great. Okay, so I wrote a slab data structure for fun, for like a concurrent thing. And here, we include heck check at the start, and then we say, hey, please, derive arbitrary for our operations. And I defined a series of operations here: insert, fetch, remove, contains, clear, and reserve. And then I set up an oracle to compare against, and our subject, which is the implementation I was implementing and I was trying to test, and then made it like generate a vector of operations. So now HeckCheck says, hey, I'll generate a series of operations, and I, in my test, apply every operation in order. And for every operation, we test that it does the same thing. So if we insert a value, it says, hey, I insert it at the same place. If we get a value, the two values should be the same thing. The value of position 5 in like our thing here should be the same value in position 5 at the other thing. And every single like operation should match. And if they diverge, then we found a bug. And so our reserve operation is pretty wonky. This is why I like never ended up using it, because I couldn't quite get this right. But like this would end up hanging because it was like too expensive. But this is a really good way to test things like re-implementations or so what is it? Rewrites, re-implementations, and data structures. You can test with this because you can have your original thing, and then you're writing a second system, and you're like, hey, is my behavior the same? You put two systems side by side, and you check that the behavior is the same for random sets of inputs. And this can be a fuzzer, this can be deterministic, this can be like a limited scope, but like, yeah, that's how you write automated tests for like complex things. In the past, I've written a memory allocator for this, like a in-process memory allocator. And it ended up that if we did something like where we created a slice and then like at a different offset deleted the thing, then we accidentally went out of range and like started writing into like the wrong sort of sections. And I was like, holy shit, what's going on? And it was like, yeah, you're not handling the zero case of a particular thing. Like the lead of zero was like broken. I was like, oh, okay. Now I get that. Similarly here, if we go through tests, then this is a differential test. And you can take this thing and be like, please, once you find a bug, you can try and reduce it down and find a like file a regression test. So here was a regression test where if we had an empty thing and we removed the zero thing, then I believe we would like go out of bounds. A different one where it was like, if the thing was too big, then we would like hit a bug. So you can use this as a driver to check in like regression tests to prevent further issues like that from happening again. So that's strategy 2 out of 3, differential testing. Then strategy 3 out of 3 is invariant testing, which invariant means a condition which must hold. So, when you're writing a test, you may have a condition like, my program should never panic. And then you can write an invariant test which says like, okay, I'm just going to test that my program never panics regardless of what input I give it. So you're writing an HTTP parser or a little web server, and like whatever payload is sent from a user, your thing should never panic. And you can just test it. You can just feed it random like input, and it'll like, should always work. Whatever the output, never panics. Or if you're writing an algorithm, you can be like, hey, whatever the case, when I call the sort function, the output that I produce must always be in order. And you write an invariant test that says, okay, I'm gonna like give it whatever random set of numbers as an input, And I can always check the invariant that the numbers are ordered at the end, right? Or, you can do other things like try and observe like memory allocations or whatever. Like just make sure the particular condition holds, and then you like give it random input and you check that the condition holds. That's invariant testing. In Rust, we don't need to do certain things because we've left shifted on that, which is, for example, memory safety. If we don't use unsafe, we never have to check that our program is memory safe because that's a given, that's a guarantee. Some other things we have as well, but not everything. This is a pretty good way of like adding those or the testing for those extra conditions that you care about, but you can't like statically define. Finally, like another little note here about like the difference between fuzzing and property testing. So they sort of come from like people sometimes wonder like, hey, isn't this fuzzing? Or like, hey, isn't property testing different? Or like, I've heard fuzzing's good. Like we should do fuzzing. And it's like, I feel like there's no real good difference between the two. They just come from different academic angles. And in Rust, you can do both with the same like sort of test with the same crates, with the same like, you can write your code in pretty much the same ways. Even the testing strategies apply to both fuzzing and property testing. So the differentiator between the two, like how I like to describe it, is that fuzzing is externally driven. So you have a driver like American Fuzzy Lob or libfuzz or whatever that is an external thing that instruments your program. Like it can look inside of your program. It can see like what branches are being hit. It can add sanitizers. It can inject all sorts of stuff. So it wraps your like binary and it does stuff with it. It runs for extended periods. So oftentimes you'll hear people fuzzing for days or weeks or months or like 24-hour fuzzing, open source things like, and it tends to be a little slower because of that, because it's like an external thing driving your program, takes longer. However, property testing is much the same, but it is internally driven. You can build a property testing library that you just include, and now you've got property tests. Important for that is I don't know how to do fuzzing on Windows with Rust. So there's a crate called Cargo Fuzz. It doesn't have sanitizer support on Windows, to my knowledge, still. So you can't do fuzzing on Windows. That's pretty hard. I used to be on a Windows machine, so I cared a lot about that. But property testing you can do okay because it's just a library. It doesn't require extra sanitizers to be installed or like run. Property testing also tends to run for limited durations. Like we'll say something like, yeah, produce me like 10,000 random inputs. And it's like, 3/4 of a second on a laptop. And it's like, whatever, like that's great. I've tested a lot of stuff. Pretty sure this is fine. Or, you run different permutations. You eventually find a bug. But you can just make it part of cargo tests, essentially. Like it's fast enough for that. Yeah, and that's the key thing. It's just so much faster. So I like both approaches, but for different reasons. I feel like if you're going from unit tests and you want to get to like that super high assurance sort of like where maybe you're like, hey, I'd like to go fuzzing, targeting property testing first as part of your existing test suite could be a very nice intermediate sort of target. I don't want to recommend you should use HeckCheck. Like HeckCheck is like 200 lines of code, but something like HeckCheck can be useful for that. So the sort of similarities between both is you can use them with sanitizers if you'd like to. You can use HeckCheck or like whatever property testing framework you like together with, for example, Cargo Meaty to test for all sorts of like safety invariants if you're using any form of unsafe code. They can both shrink test cases. So if you have a strategy where it's like, oh yeah, produce me commands, and then at some point you find a thing that like doesn't work, both like approaches will try and like reduce the sequence down to its bare minimum and then be like, hey, I found a failure. Here's the failure. Here's the seed for the failure. And then you can reproduce it. And both of them can work with structured data. This is oftentimes like hailed as like property testing structured, fuzzing is not, but it's like, no, you can do both. You just need the right tools for it. And so the right tools for that are probably the number one thing I'd point you to is the arbitrary crate, which I'll just go there. Arbitrary. I'm showing you all of my browser windows. It's just a crate here. It's maintained by the Cargo Fuzz group. I feel like we should eventually put this in the standard lib under the probably test. I'm not sure. I'm not sure whether anyone has the appetite to, but I think it would be good. And this works with both like property testing and fuzzing frameworks. Then the other thing to check out probably is the Cargo Fuzz project. So it's under Rust Fuzz / Cargo Fuzz. I don't know if you can see this. There's a Cargo Fuzzing book available here as well that has a setup and tutorial. And if you go to the section Structure Aware Fuzzing, it'll walk you through basically what I just showed you with round trip testing, but using the Cargo Fuzz framework. Do I have anything else here? Oh yeah, of course, heck check is a crate that I wrote. I sort of showed you that already. Heck check is right here. So it's the README for heck check. It's just a little fun project that I wrote. It works surprisingly well. So I used it to like, test my own like data structures, and that worked pretty well. So there's that. And the final one is prop test arbitrary interop. So prop test is the sort of the good property testing framework in Rust. However, it doesn't work with the arbitrary trait. I wrote heck check because I was like, hey, hold on. Can't we write a property testing framework using the arbitrary trait? And the answer was yes. Prop test arbitrary interop takes that same idea, but doesn't say, hey, we'll write a new thing. It says we'll just bridge the gap between the two. And that paints a potential future for like, hey, maybe we could really standardize the arbitrary trait and then build all of our like automated testing frameworks around that. Yeah. So demo time I kind of did in between, which means that's about it, what I had in terms to present. I'm very happy to take questions if anyone's got any. Yeah.
How do you, with heck check and arbitrary, decide or tell the system that there are only certain types or valid ranges, right? So you have RGB where UA is valid for all the values, but if you only have a subset that was valid, how would you do that?
Yeah. Oh, 1 second. My cat is trying to leave the room.
Deflected.
She was asleep on my desk.
Oh, it's such a really good answer. I'm sorry, you can't.
Did I dodge the question? No. So a cool thing about Rust's derive system is that derive is a way of typically automatically implementing a trait. It's a derive macro, and there's oftentimes a trait of that same name that you can manually implement. So in the case that you have like, hey, only a certain range is valid, rather than deriving it, you can manually implement the arbitrary trait, which is what we end up using, and then be like, hey, I'll constrain my ranges here. In my opinion, the ideal end solution for this, or the intermediate solution, would be for arbitrary the derived trait to allow you to constrain the ranges using patterns. And personally, I'm a big fan of pattern types in Rust, so I'd love to have first-class pattern support in Rust to be like, hey, only numbers 12 to 16 are valid for my U8 over here. That's the range. Or like, only these strings should be allowed, that kind of stuff. But that's way in the future. I think we can probably improve the arbitrary trait to support it natively in the meantime. And, right now you can just hand roll this. Yeah. Does that make sense?
Yep.
Great.
Yeah. Oh, I have a few questions, but first of all, thank you for making heck check, because I think, if I'm not mistaken, with prop test, you can't, if a test fails, you don't get the seed, so you can't deterministically replay. Is that right? I think that's a feature that I was missing at some point. And heck check does that. So that's like a selling point, I think. Just like this small
I know
feature.
for sure heck check has it.
Yeah.
I don't dare say about prop test.
Okay, I couldn't find it anyway, but so I just think that's a good selling point. But I think when you use arbitrary, that means you don't get shrinking for free, right? So is that right? There are some property test frameworks in other languages that experiment with if you specify how to generate test cases, it can specify how to reduce those. like shrinking. So you get shrinking for free is like a buzzword in that context. Is that something you've looked at?
So I'm guessing your question is, I guess I'm not sure what your question is.
If you get shrinking for free when you use arbitrary.
Uh, you don't need to do anything else to get shrinking. That is correct. You just plug and play and you get shrinking out of the box. It's not the best shrinking. Like I said, it's 200 lines of this, like, HeckCheck is super small. We could be cleverer about our shrinking. I have some ideas that I never got around to. But yeah, shrinking should be like a no issue. So all the fuzzers, they provide shrinking out of the box as well. So it's for certain like possible to do good things with shrinking that I'm not doing in HeckCheck. But I think when you say shrinking for free, yes, we do that.
Yeah. So when you said boundary testing, the first thing I thought about with serialization, especially is SERDE. This is widely used in Rust, and for SERDE you have something that is even stronger than in normal boundary testing. You have something called SERDE test, which does structural testing on them. So you don't just say it works for this serialization, but it works for all correctly implemented serializations. And that is.
Oh, I like that.
Like if it is I think that is stronger to say than just a normal boundary testing, which is quite interesting.
Yeah, no, I like that. I like that a lot. So I wrote the HTTP TypeScript. I'm the lead author on that. I don't work on it anymore, unfortunately. But something that we do there is, like, in HTTP, you can have like headers. You can define multiple headers at the same, like, here's my header of foo, and then another line, hey, it's foo again, and like both values may be like valid. And if you like parse it, you can like decide. There's rules around it. Doesn't, like, what I'm trying to say is you can simplify the representation of some of these headers. I never thought of that, so it makes sense to, like, we simplify that representation all the time. And what you're saying is like, hey, if you're your testing stuff is like aware of that, then you can just simplify it, and that is a valid representation too. That's awesome. Yeah.
We talk the test. You as it is now, you have to specify like a AST of like a token tree of what you want to think of it, and then you can generalize it across all serializers that support all servers, which is quite nice to have. Then you have big models that need to work in multiple serializers.
I'm guessing one way you can do this is by like being clever about how you implement equal or partial eq, that you ensure that you check for not like structural equivalence, but like semantic equivalence. Like, are these two types semantically representing the same thing, rather than are their contents strictly the same, like string or parsed version of that. Like, yeah, I like that. Thank you.
The other,
Yeah. So
maybe if you come close, I can't really bring this closer. Yeah, if you just like,
can you hear me?
Yeah, I think so.
Okay. So in the slide you have both the term invariance testing and property testing. So I wonder what the difference is between those two terms.
Yeah, for sure. So the question is, what is the difference between invariant testing and property testing, right? Yeah, great. Okay, yes. So how do I say this? Invariant testing is a testing strategy. You can use this with both fuzzing, like fuzz testing, and property testing. So if you think of like property testing and fuzz testing as like two separate ways of testing, then round trip testing and all these other things, they live on a different axis. They're strategies of testing rather than sort of, I guess I wouldn't say these are strategies. These are more like styles of framework. Think of fuzzing versus property testing sort of as like protobuf versus HTTP. They kind of do the same thing, but they have some slightly different trade-offs. And then, The different strategies are like, how do I build my service? More like that. And so invariant testing is one strategy of testing. It is a, yeah. Does that make sense?
Somewhat.
Not fully convinced.
Yeah.
Okay. If I guess I'm trying to figure out like what doesn't make sense. If you have anything more there, you have to like elaborate.
It sounds like an invariant is the same as a property for me. Like property is, for example, my program should never panic. That sounds a bit the same as the invariant here. But
I see.
yeah, maybe it's just semantics. Maybe it doesn't matter. It's possible.
I see. So I think I'm like too like these words. I no longer think of them as like having a meaning. They're just are a thing. Like when people see LLVM for the first time, they're like, "Oh, what does it stand for?" You know, and like someone who's been using LLVM for a while is like, "No, it's LLVM. It stands for LLVM." You know, it's its own thing. So I no longer think of invariant testing as having like it's its own thing. Property testing is its own thing. But you're like, no, 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 they're words and they have meaning. And I'm like, oh yeah, I forgot about that. I'm sorry. Um, you're right that the two things sound very similar, and I can see why it's confusing to see them side by side.
Is the idea that property testing is a super category that encompasses both variant testing and whatever you call the other two ones? Round trip and
So property testing is, you can think of it as a style of framework. So it is the way you drive your tests. So when I show you heck check, right? To make it sort of maybe concrete, is like when you see heck check, the difference between property testing and fuzzing is this line right here. Here we call heck check check, right? It's a mouthful. And that does things in a property testing style, which is short-lived as a framework, you know, or as a library, and like it'll run, I don't know, 100 permutations, and then it says, okay, good job. Whereas with Cargo Fuzz, like you know, it's its own like command line tool. We invoke an external program and we drive it differently. But if we look at the structure aware fuzzing here, then the line how we drive it is like slightly different from heck check. So that's sort of the driving framework, property testing versus fuzzing. But then the code that we write inside of the closure, it's like, this is a round trip test. And in both fuzzing and property testing, like that round trip, where's the thing? Here's the thing, right? This round trip test is essentially the same thing. It is a testing strategy that we can drive with either framework. And invariant testing is one of those testing strategies. So there's invariant testing, round trip testing. I'm trying to remember the third one. I forgot the third one. What's the one with the instructions? Yeah. Anyway, I can scroll up and just look at it. Differential testing. I'm sorry. Those are the three. Does that make some sense? Okay.
Yeah, one more.
You've mentioned that you would like arbitrary to be standardized.
Yes.
Is that that's purely hypothetical, right? There's no RFC. There's not even an alternative to arbitrary that's been developed. There's no not anything you know of that would be groundwork. How does that work even in like other languages that might be more mature than Rust?
That was just me spinning out an opinion where I'm like, I would like to see this in the standard lib, because it feels like the ecosystem is sort of converged on this. It is very small in scope. Arbitrary itself doesn't do much, and it feels like we can sort of build from there. It doesn't need to take priority either. So indeed, it's just my opinion, just a desire, you know.
Let's see, we already had this. Does anybody else have a question? No? Then we can fall back to
All right, cool. So I won't start a flame war against arbitrary because it's the wrong time to do that now. But I have another question. I played around a very limited amount with fuzz testing about a year ago, and I found a package called Bolero. I don't know how to pronounce it. Did you try that one? Bolero.
Sorry.
B-O-L-E-R-O.
What's the name of the thing?
B-O-L-E-R-O. It's like a fuzz testing wrapper. I think you can use it with AFL or something like that.
It's the first time I'm hearing of it.
Okay,
I'm
yeah.
sorry.
Yeah.
I haven't.
No worries
tried
then. I just I thought maybe it's something like that belonged to that list, but obviously there's so many things. So
Yeah.
never mind.
It's
an
very cool
advertisement.
to see like how many more projects are like being
Yeah.
spun up and how many more people there are. In the last like 3 years, I believe we like the Rust community has expanded about 20x or something. So it's like to try and keep up with every single project
Yeah.
is a lot.
But I tried
Right.
this and I on a parser it was like nothing important, but I think I found some ANSI escape sequence injection bugs or whatever. You could put some ANSI codes in my input and bad things would happen. And you know that's a corner case I hadn't thought about. Or actually I had thought about it, but I'm like, oh, ANSI malformed ANSI, that's just like bad user input. That's not a bug. And then my friend was like, no, that can be exploited. I'm like, oh. Okay,
It's a pretty common factor, but
Yeah,
you really think
but I just didn't think about it as a problem, so I kind of patched it by ignoring it. And then this fuzz testing framework went back and said, no, you don't get to choose what people exploit. And that's, I think, one of the strengths of fuzz testing is just like try everything.
I mean, you can make it easier for hackers by leaving a note in the README that says, please don't use anti-escape codes. I think that's, we're just about up on time because our food is on the way. I think that was the last question. Yosh, thank you very much again. I think, is this your 4th time? At least?
Third, I
Third?
want to say.
Okay, we're gonna have to get you one of those like stamps where like the next one you get a free coffee, I think. But yeah, we really appreciate you, like, you keep coming back and doing this. This is really awesome.
Can we bribe your mom? Like the 4th stamp is a Ferris?
I will see how much production she can spin up. She said it was really pain in the ass to make because of the shapes of the crab claws, but you know, maybe it's just work hard. No, maybe. But yeah, again, Yosh, thanks so much for being here. Let's give a big hand to Yosh before we